So, when I started this lecture series, I said it's impossible to teach construction because every construction site is different from another. And in my understanding, it's impossible to create or offer something like recipes in advance. But in the end, I thought it would also be interesting to give an inside view on what is happening on a construction site and on a very specific one from our office that we know, and that also this view should be offered by somebody that is really on site. So not by me, because as you know, I'm here and traveling to Milano, and I'm just visiting maybe 2 or 3 times the site. But in this sense, I just would like to make a short introduction for Caio Barbosa, that will take over later, and that is living now since more than 2 years in Bahrain, working on this construction site. And I will just very quickly introduce to the, let's say, history of the project. And I start with a very short description of Bahrain. It's a very small island. It's smaller than the Lake of Geneva, but it offers a lot of variety. It has 3 UNESCO heritage sites. It has, for example, the largest burial moulds field in the entire world. There's also a Formula 1 race, and so on. And the project that we are talking about and for which we made a contribution is the Pearl Path project, which is in the medieval village of Manama, that is the center of Bahrain. And what is quite unique with this project is that it brings together national heritage sites and combines it with contemporary architecture. This is now the whole walk through this medieval, or let's say ancient, town of Manama. And there are different sites that I will show very quickly later. We are actually were offered or were given the chance to make 4 implementations, 4 parkings in totally different sites with a different geometry, with a slightly different surrounding, which are connected loosely to this Pearl Path project. This is a project by Valerio Olciati, the Visitor Center in Bahrain. Another project by Anne Holtrop that was initially shown at the World Expo in Milano and was later on built again up in this old town. And what is very beautiful and unique is this implementation of new buildings in combination with old historical sites, which are partly run down and now under restoration. This, for example, is the Palace of the Winds. This is a detail from an entrance. And let's say this was, for us, the background, the context for which we would work. There are also many squares. There are several designed by Office. This is one designed by Anne Holtrop. And when we started the project, we were very actually happy, you know, to work on a parking, and the reason is that there are very few parkings that are very, let's say, that are interesting to look at. Of course, there are some, let's say, also recent famous examples that are based on very specific contexts, but what interested us most is, you know, what could be the DNA, what could be the basics of a parking in general. And there are very few, let's say, historical examples, as this beautiful parking that Melnikov proposed to the city of Paris. This is actually the first proposal that Melnikov did for Paris. And so we started with, let's say, imagining it's a very, you know, unique opportunity to start with the movement of a car and to design out of that a building. And we made many different trials, you know, with interior courtyards, with ramp being cut in many different ways. But what was disappointing about all of these studies was that, let's say, the space is always the same, you know. If no matter how interesting maybe the movement through this parking is, the space itself always remains the same. Another approach to the topic was that we were thinking of the structure, and we thought maybe it would be nice to have, you know, huge platforms only with very few columns on the outer side. And this would mean that you would have an inclination of the slab thickness. And so that you have, for example, here columns, and here you don't need any columns, so that it works, let's say, like an arch. And this was maybe a bit, in an economical sense, not the favorite solution. But what was interesting as a starting point was that you could imagine spaces changing from one level to the other. And then we thought of maybe one can combine, you know, this notion of movement and the notion of structure to become one. And so these were the very first tests, and here we were still thinking, well, maybe there's an outer wall or so, but it would be interesting to have such a ceiling, such a floor. And in the, let's say, intention to unify these different elements, we were thinking maybe the slabs, they are curved in a way that they touch each other, so that you can move with the car directly from one slab to the other. As you can see, the structural elements at that moment were not, let's say, the most important topic. But, let's say, this notion to create an ever-changing space throughout the movement of a car was actually pretty close to what later on would be built. And what also became, let's say, like a nice side effect is that from outside, this building becomes different. Each side looks different from another, so you can imagine it's interesting to walk around in this very dense neighborhood, and it's a very, let's say, open space that can be maybe also used for different things than just parking. To show you this connection of slabs, if you now look carefully at this car, This was still from the concept study. This is the same car, but now we moved one level below, and now we are looking from the next level to the same car. And as you can see, sometimes the space is expanding to the interior, sometimes to the exterior, and is always changing from one side to the other. These were the very first drawings where you see the topography, you see elements like elevator and stair, you see the movement of the car, and we found very basic ways to control the amount of parking spaces by dividing topography, parking space, and driveway. This is another plot, another parking. As you can see, the cut is done in different ways. And this is a third parking, which is very similar than the first one, but has a totally different scale. And this is the largest of all. And as you can see, for example, the connections, they were quite, let's say, idealized, imagining this as a parking with several hundred spaces. But you could imagine already there is a continuous change of space through movement. These were the first drawings. Today they look maybe a bit naive, you know, look a bit like going up and down a hill, like a stacking of landscapes. We also tried out many different ways, you know, how to connect these parkings. And in the next, let's say, schematic design stage, we then worked simultaneously on all four parkings and tried to find different ways to define these four buildings, to make them different from one another in the most basic possible way. And one of the crucial questions was how you move up. This was one of these diagrammatic models that we did. And it was mainly this movement that led to the differentiation of these four parkings. I think that is important to keep in mind, right? It's not a differentiation of a theme, but it's much more taking a concept and trying to expand it in the most opposite directions to have the biggest possible contrasts also within the same concept of these different buildings. Early studies of sweeping path, early, let's say, schemes, how to approach the question of the formwork, and also very early idea how this could be imagined in reality. When we presented the project, there was always the problem, how can you understand this thing, you know? And students would come after the lecture and say, is this serious? Is this really parking? So we thought we should explain it in a very simple way by just showing how it can be used by a car. Okay, so you can imagine. And then... Good, but this is not the topic, right? The topic is really how was it built? What is the experience, let's say, from the construction side? How was it put into reality. And in this sense, I would like to pass on the word to Caio Barbosa, who worked already several years in the office and now, since 2 years, is living on site and is making this project possible and has a much better inside view than I. Thanks a lot for joining us, Caio. You have the... No problem.
Hi everyone. So my name is Caio and I'm the project architect for the multi-story car park structures in Bahrain. The title of the lecture, Precise Roughness, is the first attempt in which we are thinking in a sequential manner through the project and its construction in what seemed most times an out-of-order process now that the project enters its 6th year in its history. Precise roughness also relates quite closely to the environment we're in. We're in the Middle East. We're in the smallest of the Arab countries in Bahrain, and we are, like I said, tasked with the mission of building 4 parking structures across 4 different locations in what is a very tight urban dense setting in Muharraq. And this is because we, and the rough and even at times primitive architecture that works as a background, juxtaposing itself with the pure concept and the kind of intention of being open in the city, also shed light on how we wanted to work in Bahrain, which is in a very instantaneous way, in a very reactive and also hands-on demonstrative manner. And this is because already since the beginning, we were entirely aware that the projects with its experimental qualities, its sheer scale, 45,000 square meters, its success would only hinge on the accuracy of a construction site, but only through the understanding of the local and available techniques already present in Bahrain. And so at the very beginning, the construction process became also about quickly identifying the very elements that are important for the project, the columns and slabs, but also the idea of a free section, which is only made possible through the movement of a car. That is the element that draws the spatial sequence, but also explains to us these slabs and their exceptions. So already in the beginning, we understood that the biggest challenge would be to, on a very basic level, maintain the 4 wheels of a car touching the slab at the same time, at all times, as the different projects presented different driving conditions, as some moved from the corner to the inside, others moved around the ramp, and again, others moved even diagonally towards the center and vice versa on a back and forth. All of this through a doubly curved concrete shell space. Also, in the beginning of the project, we realized that there was as far as technicalities are concerned, very little literature with regards to parking structures. So we started already designing our own instruments for how to measure and qualify the standards necessary to develop the design. But also remembering that we all had, at the time in the office, vastly different experiences of driving through different contexts and different slopes. In parking code, there already exists a series of grade changes which are there to guarantee the comfort of a car as it goes through the ramp. But interestingly, our design inherently dealt with this idea as the transition between the slabs would have been quite smooth. And so we positioned the ramps at the moment, the most critical distance between the concave and convex slabs to be able to enhance this idea and enhance the comfort. Another tool was the creation of what we call the universal car template, which looked at the dimensions and would later on serve as the template through which we would do our exercises and encompass a wide variety of cars that we can eventually use in the parking. So here is this template now being used, this template being used as the template that would go through the series of two-dimensional unrolled sections where we would test the inclination of these slopes. And here again another example where you see at the top where we started in schematic design, and at the bottom where we currently are on site. And what is of interest here is not necessarily that we are just transitioning and perfecting the slabs, but rather also looking at these distances where we are really pushing the limits of this feeling of entering and exiting spaces of compression and expansion. And here is what this digital construction site first looked like, where we were putting these instruments to use and testing and refining the slabs as we went along the design process. So now that we have this rather conventional method of checking the slabs, we now then proceeded with this exercise across all plots, where we would test the left and right side of the car against all the slabs in a sequential movement of up and down. And here you see, for instance, the biggest plot together with the second biggest plot, where you see a very, I really need to hold this, the gradual smoothness of the circulation of the car. And then we took these lessons and on a three-dimensional motion-based software, implemented these parameters with now weight and motion to be able to detect what is called the bottoming out, which is the critical distance that a car creates with the slab at the moment that it enters and exits a ramp. And from this exercise, we could now, in an almost scientific manner, extrapolate all of the data required and be able to locate in a very quick manner areas in which these critical points were and react accordingly if necessary. So the project, in the beginning, before arriving to Bahrain, the project, we tendered it with a very simple, reduced set of architectural details that communicated the intention. And these were laid out on a series of 1 to 100 architectural plans that at this moment really at best located and identified and quantified these elements. But this meant that all of the executive state of the project as it relates to execution design would only be developed on site. And with this I mean, for instance, all of the requirements that come with designing a parking structure, from lighting to staircase design, finalization of structural principles, finishes, handrail, mechanical, electrical, plumbing, and all of the systems that go with it, which are topics which we will not cover today but are inherent to the design. So upon arrival to Bahrain, the first challenge we faced on site was that we are building an island, and this island has extremely weak soil conditions. And where we could find water in all plots just 30 centimeters below the surface. And this means that in Bahrain, it is as per the convention that the engineers assume that the soil is weak and cannot take any loads. And because of this, you directly go to a pile foundation. In our case, the problem with this is that the pile accounted for 40% of the budget. So we had to react with the economics of the project and imagine another method, which we did by being specific to each location through a method that is called the soil structure interaction method, that looks at the relationship between the foundation geometry, the loads it presses upon the soil, and the soil reactions in return. So after this exercise, we could stipulate that now, in fact, we could do what is called a shallow type foundation. And what is of interest with this here is that now we're moving from a punctual type of structure into a surface type of foundation, which means that already at this point we can integrate the already present slopes in the ground level with the foundation. And this raft, which is the raft, right? And the raft consists of a series of square drops that were located beneath this reinforced concrete slab. And that we could, like I said, integrate already these slopes. So here, for instance, is in plot A, the moment at which the ground level slowly ramps up, which to eventually meet the first level ramp. And here you see this square, which in top view would really be a square, but now starts to deform itself against the hilly condition that manifests itself on site. And here this kind of very vast, enormous field of drops begins to appear. And in order to further improve the efficiency, but more importantly, reduce the amount of concrete and steel in the raft, we also introduced in the foundation a series of pre-stressing cables. Likewise, as we will do on the suspended slabs, to again make this as shallow as possible, because remember, we are very on top of the economics of this project. And so here you start to see what we call the engineered landscape. And this network of pre-stressing cables mostly interacts with the column grid to counter the deflections necessary. Here you see the relationship between the very thin section of the column and the enormous size of the drop, which gives you an idea of the amount of vertical and lateral loads that this very thin column needed to take and the mass required to absorb and distribute these loads. And also evident is the intensity of reinforcement around these as they near the columns. And once these drops were filled with concrete, this is the first batch of concrete of the project, we could now use this surface to fix the columns and after finally cast the raft, which includes already the initial sloping conditions of the project. And we start to see at this moment the development of the four car parking structures being constructed simultaneously in what we see here as the landscapes of concrete. And so now that the raft is in principle finished, we can begin our next activity, which is probably the most sensitive topic in the project, which is the scaffolding. And the reason why this is quite sensitive is because on the one hand, it's a very rigid system. It's an inherently rigid system. And it requires a huge flexibility, and it had to be deployed over large surfaces at once in 45,000 square meters, right? But of course, remember, the section of this project is changing everywhere. It's completely different from one place to another. So it was at this moment that we had to stop and have an understanding of what we were doing here. In the history of architecture, we find several examples of slabs, concrete slabs that are trying to take these different slopes. And many of them use the principle of what is called a ruled surface, which is a surface that is changing in its nature, but is built with straight lines. But what we have here, remember, is actually a doubly curved surface, or what you could say as an unruly surface that is built as a network of moving curves. So you see here the kind of ruled surface, very easy to anticipate, and in our case, an unruly surface that could only be logically explained through the movement of a car. And many architects have also built some slabs like these that try to take on these different slopes. But the problem is that they rely too much on digital fabrication methods like laser cutting of wood boards, or for instance, three-dimensional foam milling. And the problem is that these systems that are very precise and due to their inherent level of accuracy, they do not allow for reuse, and they do not allow for the repetition, right? But in our case, we were much more interested in returning to this idea of the ruled surface, or let's say the logical and constructive thinking that is inherent of the ruled surface, which means to work with the line. And so we set ourselves an exercise to identify the area in the entire project with the highest degree of slope changes. In this case, it's plot D, the ramp of plot D. And we very quickly, with a very short budget and 2 people in a couple of hours, we managed to build up what is the first mock-up of the project in the office and started to extrapolate some meaning out of it. So what we have here is a series of parallel guides that are equally spaced that can now begin to allow for the distortion of these elements to take place. So now what is important here is this element. This element, which at this time we did so naively, would later on become the so famous called third beam. The third beam, what it told us at this time is that this is the translation of an initial doubly curved surface into a series of 2-dimensional lines upon which we would install planks to once again reinterpret the doubly curved surface. And now that we have the principle set, the proposal was to install this rather simple and custom-made piece onto what is otherwise a very rigid and ready-made scaffolding system. But in Bahrain, the issue is that despite the fact that the construction team accepted the third beam as a principle, it is the standard in Bahrain that if there is any change in slope on a project, that they would take it with the vertical element. These vertical elements are called the standards. And what happens is that in a condition like this, and what we were trying to explain is that everything here has a different point, everything. Nothing is straight. Everything is constantly changing. And you have to remember, right, that we were just starting. So they didn't know we were talking about deploying this over 45,000 square meters. And this means that you had to anticipate the relationship between all of these elements with relationship to one another. And this is how it looked from the other side with, again, everything in a completely different space. But we still believed very strongly in the economics and the efficiency of the so-called third beam, in which we had a series of flat tables, again, with the beams on top. So we actually, in a very kind of friendly way, decided to make a quick competition where we would time ourselves with a prototype, and if for any reason this was faster, we would just do it. And already in the conclusion between the 2 mock-ups that you saw before, we can see on the initial proposal the amount of visual data that is required versus in a much simpler prototype where most of the elements have a clear relationship between one another. But it doesn't stop here, because we also noticed that the third beam in certain cases take up too much material. So we decided to further develop the system by maximizing the economics of the project. With this topic, we realized that the function of how much third beam you use is based on the displacement and the arrangement of the scaffolding tables as it nears the soffit of the slab. So we knew at this point that we had to also integrate into our design the arrangement and layout of the scaffolding tables. Here, for instance, in the workshop drawings, you see mostly looking quite good. In some areas, we could still improve a little bit more. And then the design principle for how to lay out the scaffolding tables was what we call the slab pixelation, in which we would first identify what are the most extreme sloping conditions in the project. And those that had the most extreme would then be supported by a finer grain of scaffolding tables while the bigger areas could be then surfaced with larger scaffolding tables, which we could deploy much faster on site. And so now that the principle is approved by everyone, we can then identify in the market in Bahrain the locally most widely available scaffolding tables in the country, because we had to consider that sometimes we would deploy these at 4,000 square meters at once. And so we went on to design and lay out with this principle of the slab pixelation, the different layout tables for all the slabs in the project. But remember, we did this in 2 dimensions. We did this in plan, right? So now we are missing to think about how to determine the height of these scaffolding tables relative to the floor. And this was the biggest challenge here, because we had to do it in a very fast manner. Because we had to come as close as possible. Remember, we had to come as close as possible to the soffit so that the third beam would be as little as possible. And this means that we determined already at this stage a tolerance of 50 millimeters for all the scaffold, for all the third beams to be able to be installed on site. But it was also at this moment that the contractor had, or the construction team had notified us that it would take them 12 months to do this job. And at this moment, we were just finishing the raft. We had 2 weeks to provide the construction team, the team on site, with all of the data necessary to start the scaffolding work. So I have to highlight that this was an extremely intense moment in the project, and we realized that we had to take on this challenge by quickly reacting. And the way we did this was by first understanding it as a series of constructive methods, which we would tell Grasshopper what to tell Rhino, into a recipe of 7 short steps that within 1 hour we would very quickly generate all of the scaffolding tables for the entire project and their heights, and more importantly, give them all of the third beam shapes within a very short period of time. Just so you can understand a bit the logistics of this operation, if you were to grab all of these third beams and string them along in one continuous line, you basically get 2 times the whole length of Bahrain. And now that we have this entire principle and design made, we can start to imagine how to deploy this on site. Now that the raft is covered, we basically provide the contractor with a matrix of points. And these points are quite simplistically located on site and drawn. These points are then substituted by what I before told you are the standards. These come coupled with the U-heads. And this starts to give us the first view of their proliferation on site and the first reading of the project. These are then connected with a series of aluminum channels, which are called the primary beams. And they also give us the first legibility of the elevation of what the slabs would look like. And on top of these, again, the same beam, but now called the secondary beam with a finer spacing, is placed on top. And again, this idea of the slab pixelation starts to appear on site with the varying scaffolding table heights. And here is a view, for instance, of plot C, where you see the very smooth transition between all of these tables, but that are now all entirely flat, right? And now that we have finished this rather standard part of the scaffolding works, we then can jump onto the third beams. And these give the closest legibility to the slab by connecting the scaffolding tables with what is a replica of the slab curvature. They are fixed with diagonal supports over the secondary beams. And here again in plot C, you get a view of how shallow some of these third beams are and their slow changing section from one to another. And now that the third beams are placed, and we finally can see and understand how the slab will become, we can start to cover these with the planks. as far as the planks are concerned, or let's say their relative position in the formwork sequence is concerned, their orientation had only to do with the geometry of the ramps. And this is because we did a series of geometrical studies surrounding the ramps, especially on the shoulders, where the slope is extremely high, that we identified and could compare the different sloping conditions of this linear element once placed. So we found the most optimal direction for each and every plot to be able to ease the installation of the planks on site. And this, of course, became the very granular texture of the project, which you see as you move from the pedestrian perspective on site. And we did this exercise for the two biggest plots because they encompassed all of the ramps. And here again, you see in this case, a little bit less, but nonetheless struggle in making sure that these planks are being shaped accordingly. And now that the planks are installed, you begin to see how smooth the surface visually presents itself. And in certain areas, like again in the shoulders of the ramps that are a little bit more complex, we get quite a lot of deformation. And to counter these deformations, what we do is that first the work must go on. So we isolate the ramp. We let the construction team proceed all around. And underneath the slab, we create a kind of primitive pool that we put all of these planks inside, bathed for about 48 hours. And then we bring them up again, now flexible and less rigid. We can start to bend them over these ramp shoulders. And here again, finally, the entire scaffolding formwork system completed in plot C, and they're smooth coming together. And these planks are reused up to 2 to 3 times. But to do that, we have to maintain the homogeneity on the slab. And we do so by treating the planks with deshuttering oil and cement slurry to ensure that at every slab we still maintain a level of consistency. Now that we've gone through this delicate part of the project, we can enter into the structure. As you know, the structure of the project is very familiar and simple. It's just columns and slabs. The challenge that this poses is that with projects that have so exposed few elements, you must safeguard the dimensions of the project before they quickly jump into scale. One of the things we did was to conceive of the project not as a series of columns and slabs, but also as a 3-dimensional concrete shell structure, which could take not only the vertical forces, but also the lateral forces, as these ramps being interconnected had the possibility to transfer these loads through concrete shells and through the columns into the ground. And so that this meant that we had very few details in the project that we had to control. One was the column connection to the raft, the column connection to a typical slab, the column connection to the roof slab, and evidently the connections between the ramps. In order to make sure that the calculation of the structure was, let's say, within allowable tolerances as per the architecture, and to integrate the architectural intent with the engineering approach, we shared with the engineers a series of methods by which they could start to use the already present elements in the project to maximize and optimize the structure. For instance, the evident calculating the shells as a network, coupling the pre-stressing tendons between concave and convex slabs, instead of increasing the thickness of the slabs in various different points, actually looking at the uniformity, taking special care for the connection of the reinforcement between 2 slabs, because we didn't want to double the thickness, but rather maintain the same thickness. And finally, which we used for the staircase, the concealed beams that are higher density organization layouts of rebar. And so you could, in theory, say that the project is controlled through these 4 details. On this Google top view of plot C, you start to see the reinforcement, which is, let's say, quite standard. But what is interesting here is that around the columns, you see an over-densification of the reinforcement as well as around the ramps. And this project, or the reinforcement, is made up of a series of layers. And these layers that are quite conventional are a series of bottom and top reinforcement, pre-stressing cables with the reinforcement of the columns, which are denser. But their relationship to the curvature is what is of, let's say, higher interest here. As you start to see now in plot C again, we are now accommodating for this reinforcement on the slab. Here's the bottom reinforcement slowly bending on this rather smooth surface. And of course, around the shoulders of the ramp, you start to begin to see the challenge as these rebars arrive, and we must find ways to bend and adapt into to these varying slope conditions. Because it is also at this moment that the reinforcement is of a finer grain. The spacing is much smaller, and the section at times is much bigger. And for these, they required, here you see a test, a mock-up of how to bend the rebar on site to be able to adapt to these very inclined sloping conditions. The densification and increase in size of the rebars also happens where two slabs meet each other, which this is in plot A is around this case here and back there. And here in plot C, you start to see, again, the kind of intensity of the reinforcement around these areas. But more importantly, now the pre-stressing, how it runs more freely around this. And this is the element that is important because it's what keeps the slab thin, reduces the amount of concrete needed, and also the amount of rebar. The pre-stressing cables, they run inside the slab in a very linear fashion. And they run from edge to edge, and their effect at times is even enhanced by the concavity and the convexity of these slabs as they slowly deformed, as they're only capable of slowly adapting to very gentle conditions. They need access from the side in order for the post-tensioning to happen. And this is what, for instance, one of these details looks like at times when an angle meets another angle. And the condition of this void, which would eventually appear on the side of the concrete, was also carefully looked at, designed, because of course this is engineering, but it will become eventually part of the architecture. So now that the slab reaches its required compressive strength, around 2 to 3 days after, we are ready now to pre-stress the post-tensioning cables. And again, now that we have post-tensioned these, the voids are left and are ready to be cast so that they too become part of the architecture. While in plot C we were able to use one single tendon that runs from end to end, the reality is that in the other plots we could not, because in Bahrain, as far as pre-stressing cables are concerned, you have commercially available two types, from up to 30 meters and then from 35 to 60 meters. So this means that in the case of plot A, where you have dimensions of up to 120 plus meters, we would have to coordinate what is called a construction joint. This is not a dilatation joint. This is not a contraction joint. This is nothing more than a stoppage of the works simply due to logistical parameters. And we knew that already at this moment, having to stop the pouring of the slab meant that this would have to become integrated in the design. And so we looked at a series of varying construction types of joints because as per the convention, this is usually a straight line on a slab, and you can usually see this in airports, in vast concrete slabs where you see this kind of very rigid grid. But in our case, we were again interested in integrating this with the design and bringing them in. On one of the first criteria we used was, aside from the obvious, which is curved, is the fact that we wanted to coordinate the sizes of these pores relative to the context, and also so that they had a little bit of similitude between them, so that we would develop a kind of sensitivity for the workers on site over time. again, the topic of the curvature came from the fact that these slabs, which are already curved in nature, meant that the construction joints should in a similar way mimic this by following the tendencies of the geometry. And here's a quick view of how this starts to now shape up. Of course, we will wash a bit this concrete after. And we could now start to implement this new parameter into the project across all slabs. But this, of course, meant that now instead of having 17 slabs, we have 43 mini slabs that we had to coordinate with the engineers, the layout and the position of accessing points for all of these pre-stressing cables across these 43 pores. Another type of construction joint that appears in the project is where two slabs meet. And the reinforcement is, let's say, not of interest here, but what is of interest is the fact that, again, we wanted these slabs to come and to maintain the uniformity of 280 millimeters in profile. And so we had to very carefully consider the construction sequence or the pouring sequence between these two slabs. And so we set out, again, another exercise with the construction team where we would show how the reinforcement of the slab below with extended length would be left exposed, and after it would be cast. Then after the slab is cast, we can bring in the formwork of the level above with its reinforcement, and then we can now fold into it the reinforcement of the slab beneath, so that we can maintain here a kind of, this slab would come up to halfway and this slab here the other half. So the slab below at this moment is cast only up to 140 and the other another 140. On site, the way this plays out is by leaving a kind of provision, a formwork provision in which the slabs, in which the reinforcement are left exposed upwards until the moment where the reinforcement of the slab above connects with it, and we can now fold those again back into the additional reinforcement. And of consideration here and importance for this detail is only the specified extended length of the reinforcement as they reach and grab into one another. Aside from the openings in the ramp, we also have the openings of the elevator and of the staircase. The staircase is a spiral staircase that is both hanging from and supported by these doubly curved shells. And this was mostly possible due to the implementation of these concealed beams that are coordinated with the eventual position of the staircase landing, and from which you see a series of reinforcement that jut out from the slab reinforcement through the concealed beam into the landing. And so the staircase must act in this case as a spring. And this spring, as we were discussing with Mario Monotti in several instances, was conceived as a series of thicker rebars that go on the most outer and most inner parts of the staircase, and which would then be able to counter the deflections of the movements of one concrete shell above and one beneath. And we also assisted the deflections by, in some cases, introducing quite different layouts of pre-stressing cables, again enhanced by the concavity of these slabs. And the staircase itself, with its own challenges, brings in the geometrical and the multi-story challenge, which is that it is departing from a doubly curved slab, landing onto another doubly curved slab, which means that the spiral staircase is also doubly curved. The soffit, at least, is also doubly curved. And this required a very close coordination on the different points of the bottom part where the reinforcement is. And the formwork, in a kind of very precise way, adjusts itself depending on the settlement of these two slabs after they're cast. And the formwork of the landing, which works with the same logic of the slab as a continuous smooth surface, and the formwork, which you see here, the effort in trying to adjust to this now new doubly curved surface. the reinforcement, which can be quite tight and dense here, on a condition like this, reacted quite instantaneous reactions on site, with also the engineer to be able to accommodate for these changing slope conditions. The staircase was thought to be cast in 2 parts, so at the bottom we could freeze the reinforcement and only later cast the steps more carefully. The columns in the project were thought to, in a way, enhance the expansion and compression effect of these shell spaces. And we did this by doing 2 things. On the one hand, freeing the elevation or the facade of the project with these columns, which meant bigger cantilevers. And on the other, increasing the distances between these elements, which in this project at times, at an average, is between 11 and 12 meters, and in some cases even up to 14 meter spans with a back span cantilever of 4 meters. This means that also in some cases we even get columns that, because they skip a level, we have some slabs that don't go up into the end, that we would now introduce a new parameter in the project, which was the issue of slenderness. In which some columns can achieve heights of up to 8.5 meters without one single connection. So with the engineer, Patrick Gartman, in the early stages of the project, proposed and was pushing quite a lot for the idea of a composite column, which is a steel pipe that is filled with reinforcement, rebar, and high compressive strength on the inside. And this composite pipe would allow for us to maintain the span and also address the issue of slenderness. But when columns connect to slabs, they must act as if they were much bigger inside the slab than what you visibly see underneath it. And this has to do with the phenomenon of punching connection. The punching connection is what, when the column is responsible for taking all the shear forces of this moment connection between the slab and the column. And in most cases, as in parking structures where the loads are so heavy, this detail can become so huge that they supersede the thickness of the slab and become visible at the bottom. But in other cases, when you want to conceal this detail, you must go for a kind of extrusion steel profile that departs from the center of the column and is further extended by a series of dense rebars. So at this moment, we had to also think about how to conceal this detail into the slab. And at this moment, we thought that instead of working with a line or an extruded steel profile, we would switch the thinking to a surface, or at least to a couple, to 2 surfaces working together as a punching connection. But already here you see the initial problem is that in some cases, or in many cases, the steel plates went straight. Even though we try to accommodate for this, they start to protrude out of the slab. And so we switched the thinking and said, okay, let's actually make them then offset from the slab. And we actually tried this process in identifying what the different heights between the 4 corners of the steel plate would be and imagining how the steel plate could deform accordingly. And here's a view of the first prototype where you start to see evidence of the struggle in bending these plates. And we managed to do this by casting steel on sand formwork. So once now that we have this principle understood, we now have to play it out across all columns of 4 slabs, of all slabs. But it is also here now that we understand that the vast majority of the connections can't be actually not curved, but rather if you just carefully arrange them in an inclined manner within the thickness, you can in fact keep them flat. So then we have to now just finish the integration of this punching connection with the varying reinforcement requirements of the slab, with the pre-stressing and the additional reinforcement of this punching connection, which is to come. The detail looks a bit like this, where the bottom plate the one responsible for taking the shear forces, and sometimes can go up to 1.5 meters by 1.5 meters from the center of the column, receives a series of bolts on the top, where half of them, the shear studs, are only there to increase the friction of this punching connection, while the other half is used for the eventual fixation of the top plate, which is also part of the punching connection, but that serves as the fixation base plate for the subsequent column to come on the top. Finally, to close the constellation in the punching connection, we have the shear keys. These guys appear in the moment when the reinforcement surrounding the punching connection is placed, and they are responsible for quite literally holding on to the reinforcement of the punching connection, and on the other hand, connecting to the reinforcement that now comes from the slab itself. But remember, while the majority could be flat, many had to be actually adapted to the curvature. And so in a similar way, we proposed a series of folded metal plates that were welded together, and here you see the effort in doing that and ensuring that all of these parts would come together, and their elevations, of course, ever changing as you moved around them. Here's a view of these steel plates, one of them on site installed, and at this moment also we were receiving the column from the top, and you see here the base plate where it's ready to be fixed with the bolts from the top. So now that we have discussed most of these things, I think we can go on a little bit into the concrete pouring. And the concrete in here is important because, we must remember that we are in the Middle East area. And here you have very brutal conditions for fair face concreting. We have an average temperature of the year of 30 degrees, extended summer periods of up to 7 months that go in the solid 50 degrees Celsius. We have a very challenging urban fabric to navigate through with the resources coming in and out. We also have fairly large pore sizes, varying reinforcement types of arrangement, and more importantly, we have completely different sloping conditions across all slabs. So, of course, we did a lot of mock-ups, and on the one hand, we were testing the architectural intent and the aesthetic finishes, but more importantly, we were interested in simulating the site conditions that we cannot control, like temperature differential, sloping conditions, humidity level changes, troweling techniques which must be changed from 1 minute to another, lack of workmanship available, and even the different times in which concrete settles. So this meant that we had to get quite close to the very basics of this concrete recipe and design, at least in the beginning stages, 2 types of concrete recipes, one which would work for the, let's say, flatter areas, and one that would work a little bit for the most inclined slope areas. And always paying special attention to the relationship between the top surface and the soffit, where this became a function of how you treat the formwork with milky cement, with different types of milky cement composition, release agents, and so on. You see here in the beginning, actually, one of the first 2 mock-ups we did, where you see a drastic difference between them that came literally from the same day, but different batches, but that we would later on increase the precision and achieve a kind of quite good control over the consistency across the 4 plots. So with these lessons now, we put them all together in a kind of manual for concrete, which we shared with the construction team, in which we documented how you treat the formwork, how you concrete, how you cure the concrete afterwards, how to do cuts in the formwork, and even questions of scheduling and pre-stressing. Because at this point, despite the fact that I'm only talking about the kind of long lead items of the project, I don't want to also forget that there are many other steps and processes involved up until the moment we reached on site, right? And for this, of course, I had Dennis with me on site for over one year, helping me manage these sites and also set out all of the different phases of the process, like scaffolding beams that we covered, but also the mechanical, electrical, and even plumbing planning, which were required for the project, how to build the lighting, how to coordinate all of the points on site, the many types of official inspections that take place on site, and finally all the bureaucratic work that comes with it. As far as the calendar goes, we were quite interested in keeping a tight attention to the progression of the 4 plots which were being built up at the same time across these 4 locations, because with regards to concrete, you have many types of activities, and we wanted to ensure that not only they were being followed, but rather that we could find moments of efficiency that we could overlap these activities. And now we go a little bit more into the concreting. Here is plot C. This picture was taken 5 minutes before we started concreting. And this is what we called the mock-up building. And this is important on a strategical sense because we had 4 plots, but this was the only one that had only one suspended slab. So we decided with the contractor to say, look, this is the biggest pour. This pour, it will be the biggest of the entire sequence of suspended slabs. If we build this, it means that we not only can do the job, but it gives also the trust and the confidence to all the members involved in the project that now the project is ready to go on by itself. This was cast all at once. And just to give you a sense of the scale here, we are talking about 900 cubic meters of concrete being poured all at once through coming in and out of 140 trucks with 150 men over a period of 26 hours non-stop. And the initial coordination of, for instance, at the beginning of this pour in particular was to start with the 2 shoulders of the ramp, where you have one team on one side, one team on the other. And the precise choreography due to their position in space of the 2 pumps was highly coordinated so that we wouldn't have problems, right? So now that we've gone over, let's say, the first one, plot C, we have to move on with the next. But remember, we agreed with everyone already that we have 43 pours instead of one pour per slab, right? Instead of 17, which of course means we have 43. And then we worked quite closely in designing a timeline schedule for all of these pours based on several conditions and requirements into a timeline of events where we would control and document all of the steps taken for each of the pours, so we could take these lessons into the next ones and better, hopefully, the process of casting the project. One curious moment in the development of the project was that early on we got a quick sensitivity that because the contractor wanted to, well, it was a requirement that we had to build all 4 at the same time, which was very good, right? But the contractor initially was thinking in blue here, which represents the construction site team, that they would move across all sites over time. And we knew that if we followed this trajectory, we would be ending somewhere with just the concrete casting of the slabs 1 year, more or less, from now. So what we did at this moment was to try to find means to explain to the contractor that if we, instead of procuring one construction team, one subcontractor team, and procure 4, we would be able to have each of them manage the site independently so that it's much easier to help and assist them to overlap the activities within one plot, and eventually we're quite close to finishing the vast majority of these concrete slabs within the next month. One of the logistics, of course, of building in Muharraq is that you have a series of tightly packed buildings surrounding these plots, which leaves very narrow streets for the movement of the urban traffic, let alone that of the concrete pumps that need to come in. And again, 4 different sites in 4 different locations, right? Here you see a bit the kind of logistical nightmare that this was. In dashed blue is the plot, is the area that we were given for the building. And as you can see, the building occupies 100% of that line. And in blue hatch here is the area which we were officially given to put the material, the resources, and even the trucks, which meant that we would have to negotiate with our neighbors at every floor, possibilities to kind of momentarily take over residual urban space. The constraints of the site and of the pouring conditions, of course, meant that we had to be very precise in how we orchestrated this process, and we looked quite closely at the number of the area with respect to the amount of concrete required and the number of trucks that would come in and out of the city. We also looked at the relative position of these trucks to the pours to make sure that their points of exit and exit would not create congestion and delay, for instance, the provision of concrete on site. So we always had extra batches of concrete ready to go. And this also meant that we were calculating quite closely the number of people per pours based on the different activities required so that they too would work somewhat in a linear fashion. The different activities on the site, because of the many activities on the site, it meant that we could also, for instance, find potential of overlap between the men on site. So people, you see here one pumping area surrounding the columns, another one for the bigger slabs, some people vibrating, other people taking care of the electricity provision, other people start to begin to do the rough troweling. And we also had a back team of people that were, on the one hand, doing the work, but another team that were basically inspecting the levels, which of course were of high importance here. The levels were achieved by a series of reinforcement bars that were placed always normal to the surface on a grid of 1 meter by 1 meter, but that around the ramps we would increase their density. And you see here how they are, and then after they are reached, the level is reached, we can now grind it and quite literally bury it in the concrete. In some areas, in some pours, like this one where you have ramps, this means that you have another kind of challenge, which is that you will have eventually very fast changes in slope conditions. And for this we were calibrating the time of concreting in the flatter areas versus in the ramp areas, so that we would not have a high time of settling for the concrete, which means that if we are casting the flatter areas and move on slowly back to these areas, that we would have to take special care for the vibration so that we keep the homogeneity of the slabs beneath them. In many cases, we actually cast at night. And because of that, we were separating the types of night activities in the flatter areas also. So this area here was cast when we didn't have natural light, and we would leave the areas of higher precision required during the hours where you could see and become more aware of the surroundings. Inevitably, the concrete types we used several. Mostly because in some we wanted to concrete large areas, which means that we wanted to discharge the concrete as fast as possible, right? And on the other hand, we needed a type of concrete which gave us extended hours of workmanship, so it doesn't dry so fast. And in other areas, like in the columns, we were using a kind of varied type of liquid concrete so that it could enter these areas of high density of reinforcement. So here is a feel for how the concrete we designed for the bigger areas of the slabs feels almost like a nice milkshake where the cement, the water and the aggregates flow continuously all together. And here's a look at what the very liquid type of concrete with 10 millimeter aggregates looks like to enter all of these deep crevices in the reinforcement, but that coupled with the vibration would be possible. Another condition in the slope was how to prevent the concrete from sloping really fast or from free falling. And the way we did that was by introducing a series of parallel chicken wire meshes that would retain the concrete as it falls, so that we could just slowly vibrate it to avoid bubbles and cavities and other types of honeycombs, which are, of course, not desirable. Remembering that we have, in some cases, ramps or shoulders of ramps which were in angles of 60 plus degrees. The ramp area was marked on site by a simple outline, that marked the intersection between two levels. These were isolated so that we would pour only around them, so that later on we could cast the remaining slab together with this. And remember, the reinforcement sticking out here would become folded with it. And now you get the feeling for how at the point in which the concrete starts to reach a nice settling time, and we can start to trowel. For the bigger areas, we used a standard helicopter. We did several exercises in which we didn't notice any change in undulation, so this was fine. But also realize here how efficient this site is running now. With just 4 people, we are managing within a very short period of time to do the vast areas of troweling. But there are in other areas also where you have these guys that are taking care of the troweling of the concrete as it reaches the very edge of the formwork to ensure a kind of smooth curvature and reading of the facade. Finally, the curing of the concrete, which was let's say, a curious moment here, where because of the conditions we are in, you want to, of course, ideally submerge the concrete into water, into a pool, right? So that the concrete doesn't shrink prematurely and doesn't create cracks. But of course, we have slope slabs, right? So the water never stopped on the slab. And it is, as the convention in Bahrain, to use a geotextile, which you would water, and hopefully it would keep the concrete under a relatively constant temperature. But in the first pour, we noticed that we started getting insane amounts of graphic marks over the concrete. So immediately we had to react and find a solution. And interestingly enough, it came to us when we were washing dishes that a sponge, which is not a conventional ready-made product for this type of work, would be the most adequate, because you can pour water on it and it would slowly release the water and also adapt to the varying sloping conditions on the site. And now the only thing that was remaining was to find someone who could give us 20,000 square meters of this foam. And surprisingly, we found a provider of mattresses who was willing to slice foam mattresses into thin pieces of foam. And now we can start to see to conclude a bit, the development of the project. Here in plot A, this is the main, this is actually the main street. This is the main street cutting through Muharraq. So you see how small this is. And you see the appearance of the very first big shell space and the scaffolding tables for the subsequent floor, which at times had to actually span varying heights. This is plot D. From another angle also here, the scaffolding, which appears quite fragile, giving some legibility for what's to come, and creating also a lot of curiosity in the city, And the slabs, of course, despite the fact that we go pour by pour, they grow slab by slab, of course, slowly reaching higher levels. This is a picture just taken 5 days ago, where we're just ready to cast now the 3rd level of plot D. And now you can start to see evidence of how the project begins already to make part of the urban fabric and situate itself in the context with respect to heights, distances, almost similarly to even how the surrounding buildings are doing, and these views that the building offers and kind of frames of the surrounding. And in the ground levels, always the kind of effect of having this huge volume pressing upon you, already beginning to announce the spaces that will expand and compress variably throughout the sequence. We were just beginning to deshutter one of the openings on the second level of plot A to inspect a bit what was happening. This is plot C now with a little bit more definition. You start to see the final texture, the color of the columns, the LED strip which follows the car path, the handrail detail, which we worked quite closely with Evan Kostic, an engineer here in Switzerland, who helped us through a series of different car crash tests come to the ultimate design of this handrail, which also wants to be doubly curved in nature because it's following the topography of these slabs. And you see here how the cars now, the presence of these elements, in a way almost starts to also give you indications for how the slab also behaves, or at least the ground level wants to behave. This is the first ramp in plot C that we cast, but you see here already some of the finishes, the car path. To mark its presence, we were sandblasting it after the concrete was cast, which means to remove a very thin layer of concrete from it. And here the introduction of the handrail, changing its curvature throughout the perimeter of the project. And now finally the project can coexist in the context of Muharraq with all of its certitude that it will also be developed and adapted as the people begin to use it and begin to find new ways of appropriating from these ever-changing curves. Thank you. Should I?
We still have time for questions, if there are any. Yes?
I was wondering, because the purpose of the car parkings is that they can also be multifunctional, and I remember that you said that you included things like sockets and stuff like this, but you didn't show a detail or something.
Yeah.
How are they fixed on the structure?
Yeah, it's true. Well, initially the parkings were conceived as pure parkings, but as the project hit ground, it became evident that as these were appearing as the kind of only or few public spaces, shaded public spaces within this dense Muharraq, that there would be an opportunity to think about how these slabs could work as platforms for other activities. And we did this in a multitude of ways. One was by having a series of electric provisions which are concealed within the wheel stops of the cars. So if you have a wheel stop, if you turn the cap on one of the sides, you can charge your phone there. We have also provisions in the concrete slab for charging cars electrically. We also have different types of studies or different type of light conditions within the project for activities like book fairs or call for prayers or just people coming together for different activities. And we thought about the circulation also of these staircases and their position relative to the urban context, based on also bringing a large influx not only of cars but also of people, and imagining how these spaces could be conceived. And this is actually a question that we are still, let's say, refining. And now with plot C that is already functioning, we can begin to see evidence for how some of these activities and others can be incorporated.
Or should I say something?
Yeah, of course.
I mean, when we started the project quite a long time ago, you're Brazilian, right? You came from Harvard, and Kaya was ideal to work on the project because he could do all these shapes on the computer, right? And now that I see on the construction side, I think it's really interesting to see how on the one hand side, the planning is totally depending on the work and training of the computer, but the implementation would not be possible, let's say, with robots. It would be not possible, let's say, with perfect management as you maybe can learn it and at school. But it's really just in very proximity with these people on site that this was possible. And I remember, for example, last time I was there, you told me all these small elements that are called the third beam, you know, which is, I would say, also invention, can be reused. So what normally is done with, let's say, 3D forming is a huge waste of material, right? And here also because of the pressure of economy, you know, developed actually something that is using, I would say, 90% just standard elements, you know, that are used for any other building. But adopting these standard elements, I think that is the also achievement that you managed on site. But also construction sites in Bahrain and also in the Middle East, they are run with a large number of people. And I think through this, let's say, also complex geometry and form, their work is also really needed, right? While there are other sometimes sites where you wonder, why are there so many people there, right? And I also had the feeling when I was there, not only that you had a very close understanding of them and relationship with them, but also that they were quite proud, you know, that they did something that otherwise would not be possible without this large amount of people. So bringing these two, let's say, very specific conditions together, you know, the planning on the computer and the way how construction sites are running in the Middle East, I think that is what is also very specific in this project. Good. I don't know.
I mean, if anyone has any question that is simple, or please feel free. There's. Nevin, hi. Yeah, it's the bringing together of the intelligence of program with form and structure, all within a very pure sequence of elements.
Okay, maybe just a final sentence. You know, maybe some of you think, okay, it's a bit exotic, parking and in Bahrain and so on. But I truly believe what this is an example, what this example stands for, you know, a lot of it comes from very, let's say, simple thinking, right? And much more in adapting to the situation than going there and say, we know it all from before, you know. And in this sense, I think this should also give a confidence, you know, to everybody that studies here. Kayo, thank you so much.
Thank you, Christian. Thank you.